Okay, so we have success versus failure, and again, it's what we're looking at versus what we're not looking at. Okay, I don't like those words, but that's how they define it. Okay, and the random variable is the number of successes in a given trial. Okay, so we have the formula here. NCR. Okay, so the N is the total number of trials. Total number of trials. And by the way, when we did uniform distribution, which was 4.2 yesterday, right? That's only one trial. Okay, so that was always one trial only. Today's lessons, it's multiple trials. X is going to be the number of successful trials. P is the probability of success, or the probability of what you're looking at. And I'll explain that with examples. And then Q is the probability of non-success slash failure. Okay, so n total number of trials, x is the number of successful trials, so what you're looking at. And P is the probability of success, and Q is the probability of not success or failure. Okay, then we have an expectation. So we had the expectation formula in 4.2, which was that sigma. Okay, that one kind of looks like a funny E. Okay, so this one for binomial n, the one we're going to do after hypergeometric, it's this n times p. So the number of trials times the probability. So number of trials, so the n is still the same. So number of total trials and the p is still the same. So probability of success. So n is the total trials and p is the probability of success. And why not have this down? Varies. And why not have the expectation down? Okay, a card is repeatedly cut from a deck and replaced. Okay, so we have to replace, so then we know it is independent. So one trial will not affect the next one. What is the probability that in 10 trials, an ace is cut? So we have 10 trials, so we know it's going to be binomial or hypergeometric, okay? But it's replaced, so that means independent trial. So independent. And we're doing probabilities, so we're using the formula. So we have NCR e to the power x q to the power, sorry, NCX n minus x. Okay, n is the number, sorry, so n is what in the question? Total number of trials, which is? 10. So we get 10. Okay, x is the number of successful trials. So what are we looking at? We want an ace to come up once. Okay, so we want the ace to come up once, so we only want, our x is just 1. So we want 1 out of the 10 to be an ace. Okay, so 10 choose 1. Okay, now the probability of success. In this case, let me ask you, what would be our success in this case? What's our success? What are we looking at?
1 ace.
We're looking for the aces, right? So if we get an ace, that's our success. If we don't get an ace, that's considered our failure. That's why I don't like failure. It's just, we didn't get an ace. So we get an ace or we don't. Okay, so what's the probability? What's the probability of picking an ace out of the deck of cards? Okay, you have it? 4 out of 52. Okay, because there's 4 aces in the deck out of 52. Okay, so 4 out of 52. Okay? Or you could write 1 out of 13. 1 out of 13 is the reduced form. Okay, I'll leave the exponents in a second. So 4 out of 52 is success, because we're looking at aces. What would everything else be? Sorry? Who said it? So 4 to 52, so what's everything else?
Would it be 10 minus 1?
Sorry? Can't hear you. Yava?
48.
48 out of 52.
Yes.
Okay, so 4 to 52, everything else is 48, so it's everything else except for aces. And then your exponents, so just follow here. So the 1, x is the same x, right? So we have the exponent of 1. And then the exponent on the non-success is n minus x, so 10 minus 1, which is 9. And now solve. I have it here, so I have 0.37 or 37%. By the way, it's okay to put decimals in here. So if you did 4 divided by 52, you can figure out the decimal in here if you want to. Okay, now we want the 3 aces. So out of the 10 trials, we want an ace to come up 3 times. So from 10 trials, you want now 3 aces. So 10 choose 3. The probability doesn't change. So 4 out of 52 and 48 out of 52. Okay? Or you could do the reduced form, 1 over 13, and the other one would be 12 over 13. What are my exponents going to be on each one? What's the first one? Sorry? 3, good. So my first one is 3, and my next one is?
No, 10,
7,
7.
subtracted, good. And we should get a probability that's lower, because have 3 aces out of 10 is a less chance of happening.
Wait, sir, how do you get the exponents again? Like what numbers?
So whatever's here, so this is x, so x goes here.
Oh.
So 1 and 1, and then this one is these two subtracted. So 10 minus 1 is 9. So again,
Okay.
3 and 3, and then 10 minus 3 is 7. Yeah.
How do you multiply exponents in fractions?
Just put, there's a button in your calculator, it has the power button. You have your calculator?
Can I do, if I, so, can I do 4 divided by 52 and then take that to the power of 3?
Yep. That works. And then multiply by the next one. Yeah, so you guys should try it out on your calculator. Everyone get it? Got there? I have the answer, so I'll get it out. Shit.
I have 0.031.
Yeah, I got same, 0.03, good. So 3%. 0.03, which is 3%. Good.
Oh, wait.
Okay, Ms. McKenzie has 4 children. I do not, it's just an example. Consider the probability distribution for the number of boys in family. I come from 3 boys. I have 2 brothers. Me and my 2 brothers. How many siblings do you have?
2, 1, I have 1.
I have 2.
Two, two.
I gotta look at you for a second.
Right?
1.
1 sibling, the 2 of you guys together?
I have 2.
2? 1, 2, 3. One more than 3?
You have 2 brothers?
Yeah.
You have 4 more.
2 brothers, and then I have a half sister. My dad comes from 12 though.
Oh my God.
It's crazy.
What is my mom?
Yeah. So is your mom?
Yeah.
Who's that? Yeah, 12?
Are you Europeans?
My dad comes from, I think, 7 siblings. Yeah, my dad
Seven.
has 9.
My dad has 2.
Yeah, I have 1.
Wow.
Are you European? Is that why?
All right. So first one, identify the discrete random variable. So that's the number of boys. Okay, so the discrete random variable, Natalie.
Sorry.
Okay, the discrete random variable is we're looking at the number of boys. So it's what the random variable is, what are you looking at? In this case, it's the number of boys. So you guys can just write that in, number of boys. Okay, B says calculate the probability distribution. Okay, so key words there. Keywords.
Probability distribution.
Yes. And what does that tell you? What's the hint with that from previous lessons? So when you see these two words, you have to do something. Logan? Make a chart. Good. When you see this every time, so make a chart. Okay, so even instead of here. Okay, it means a chart. So the chart, it wants you to list out all the possibilities. And then find the probability of all those possibilities. Okay, so what are my possible outcomes if I had 4 children with regards to the number of boys? How many could I have?
4.
Okay, I can have 4, yes. I can have 4 boys.
0.
I can have 0, so everything from 0 to 4. So I can have 4 children, I can have all girls, so that'd be no boys. 1 second. Mr. Mackenzie. Hi. Yes. Okay. Okay. I will. Okay, after we're done the last thing, go again. Okay, so we can have from 0 boys all the way up to 4 boys. Okay, so 0 to 4. So I get that. I can have all girls, or I can have all boys and everything else in between. Okay, so now we have to do the probability. So these are multiple trials. So having a child 4 times that we consider trials. Okay, so that's why it's different than 4.2, which was uniform. So they said if they spun a spinner once, another one, the spinner, if we do it once, what are my probabilities? Okay, this one is multiple children, so those are multiple trials. Okay, so then every child is independent of each other, so that's why we're doing binomial. Okay, so how many trials, in this case children, do we have? We have 4. So we're going to 4, and now we're going to choose, in this case, 0 for boys. So we're going to choose 0 boys.
You're so popular today.
Apparently. Ms. McKenzie. I'm well, how are you? Good. She is. Yeah, it's about 30 seconds ago. Yes, yes. Okay, got it, yeah, but it's still, probably 10 minutes. Okay, so for choose 0, okay, and then here, in this case, the success is males, that's what we're looking at. I don't like it to say success, so we're looking at males, so that's this bracket. So what's the probability of having a male? If I have a child, what's the chance? 1 over 2, 50%, right? So it's either boy or girl, 50% chance. So I can do 1 over 2, or I'm just gonna change it up, I'm gonna put decimals this time. 0.5, it's a little bit easier to punch in the calculator. So you can put 1 over 2, and then probability, what we're not looking at, which is females here, so 0.5 as well. So 50-50. That's not always the case. Certain places in the world have a higher percentage of males or females. Anyone know an example of that? I went to, this was really young, St. Lucia when I was young, one of the Caribbean islands, and the ratio of males to females is 8 to 1. So for every 8 females, there's 1 male. So their population is dominantly, most dominant is females. 8 to
Why
1.
is that?
I don't know. Australia for a year. I did my teaching degree there, and there was a place in Australia that has something like that. So it's called Perth, which is all the way on the west side of Australia, and they have a ratio something like that for males to females, like 2-to-1 or 3-to-1, which is lopsided, right? Okay, and then our exponents. So again, the x is here, so that goes on top of this one here. So carry the 0, and then the second, on the second one, 4 minus 0 is 4. And now we're just gonna fill them all in, so increasing. So 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. So 4 choose 1, probability doesn't change, just we're gonna change the exponents, that's all. So 1 and 3. This comes 2 and 2, 3 and 1, and 4 and 0. Can I have all the answers here? So I'm just gonna write them out. So to have all females and no males, it'd be 0.0625, or you could just say 6%. One male, 25% chance. 2 males, 2 females, 37.5%, or 0.375. 3 males and 1 female is 25%. And lastly, 4 males and no females, 0.0625. Okay, now the expectation, so it's just E of x equals n times p. So the saying is, if you had 4 children, how many males should you expect? So it should be easy. What should we expect, guys? If you have 4 children, how many males, how many females? Okay, 2 and 2, right? So 2 males, 2 females. That's what we should expect. So when you're doing the answer, you should get 2. Okay, so n is the number of trials, which is 4. Our probability is a half. So 4 times a half is 2. So the keyword there, expectation.
Wait, where did you get 0.2?
Or 0.5.
Just that's the same p as up here. Same p.
Oh, yeah.
So whatever this p is here. Okay, or just the probability of having a male. quality control inspector selects 20 chips for testing. This would be awful if this was a company, 10% failure would be awful. It's 1 in 10 doesn't work. Okay, so A, what is the probability that more than 2 of them are defective? Okay, more than 2. So that means out of the 20 that we choose, what's the probability of having 3, 4, 5, 6, 7, 8, 9, all the way to 20? So 3 or more. Because it says more than 2, so it'd be 3, it would be more than 2, all the way up to 20. Okay? So when we see these questions, more than or at least, we've done some at least 3, there's 2 options here. So 1, you can calculate the probability for 3, 4, 5, 6, 7, all the way to 20. Or, what can we do instead? Sophia?
Calculate the probability of 20 and 2 and then subtract them.
No, not kind of on the right way, but not, your 20 is, you're thinking about the total, right? So we're thinking about the total, and then we're gonna subtract, you're close, you're on the right path. We're gonna subtract 2, what else? Okay, 1 and 0, okay? So instead of doing 3, 4, 5, 6, 7, 8, all the way to 20, that would be a lot of calculations. Imagine writing that, and doing that one like 17 times, okay? So what we can do is get the total, in this case it's probability, so the total is 100%, and then subtract 0, 1, and 2. So the total minus, we're going to subtract 0 defects, we're going to subtract 1 defect, and then 2 defects. So defective chips, I'll put DC, defective chip. In this case, since it's probability, your total is 100% or just 1. Okay, we'll work with decimals. So 100% as a decimal is just 1.0. Okay, so now we're going to plug it in. So let's plug in these numbers. Okay, so we're doing the NPX. So what's the total number of trials in this case? What's the total number of trials? Okay, 20, right? Because there's 20 chips, so we're taking out 20. So each one's a trial. In this case, the first one we're going to choose 0. So I say no defects. Okay, this is where the wording gets kind of funny, because the first bracket is the probability of success. In this case, success is the failures, which is kind of weird. So what are we looking at? We're looking to see how many chips are not working, okay? So what's the probability that it's not working? It is? 10%, yes, so 0.1. Okay, because we're looking at the number of chips. So the probability of we're looking at the defective ones. So the probability that it's defective is from the question, it says 10%. So 0.1. That means, what's the probability of not being defective? 0.9, good, so 90% or 0.9. And then again, same with the exponents. Our x is 0, the first one's 0, and then 20 minus 0 is 20. Okay, and then we're going to continue it for 20 choose 1 and 20 choose 2. these answers written down, so I gotta calculate them. 22 zeros is 1, by the way. So power of 22. Okay, so I got all three, and when I subtract them, I get 0.3232, or 32%. So there's a 32% chance that 3 to 20 chips will be defective.